Bienvenidos todos y muchas gracias por conectarse con nosotros el día de hoy, en esta segunda sesión del Financial Challenge dedicada a analizar y a entender el impacto que tiene la metodología del Machine Learning para el mercado financiero internacional. Este webinar lo podrán escuchar en español y también en inglés, seleccionando en el panel de opciones de Zoom el botón de lenguaje. Les queremos recordar también que podrán acceder a esta grabación completa en events.vmetrix.com, vamos a repetir, events.vmetrix.com y en las redes sociales oficiales de VMetrix. Los invitamos desde ya a enviar sus preguntas en el chat para nuestro invitado y panel de expertos de la compañía. Queremos comentarles que vamos a realizar un sorteo de la última edición del libro Machine Learning in
The
Business,
latest edition of the book Machine by our expert and main speaker today, Dr. John Hall, among those who remain connected to the entire webinar. Now I will leave you the Chief Revenue Officer of VMetrix. Welcome to the second webinar of our Financial Challenge series. As VMetrix, we welcome your participation in a new, unique, and exclusive masterclass for the international financial market by Dr. Jin Sahal, where we will address the challenges and impact that machine learning is having on the management of investment portfolios. This discipline is particularly relevant for our company today, as we are about to present to the market the first and only SaaS solution to streamline the complete management of investment portfolio. VMetrix will be a game changer as it aims to change the paradigm of how the investment cycle for financial assets is managed today, providing a world-class system that includes 95% of the financial instruments with preloaded data and ready to be used in international markets. Our solution seeks to facilitate the access to all types of institutions to the digitalization required for their operations without the need of invest in infrastructure, delivering a ready-to-use solution. As a matter of fact, our software will be the first world-class to include machine learning models to detect unusual operations and generate alerts with updated information that the client can use to take timely actions and thus minimize potential losses. The international economy is going through a complex time. Signs of recessions are already a concrete reality that is manifested itself, for example, through high inflationary levels and large increases in interest rates. In the case of Latin America, one of the main problems faced by financial institutions is the fact that they do not have all the necessary information to generate investment analysis. In this scenario, machine learning model provides proprietary indices and metrics that the client can contrast and compare with the data provided by the risk rating agencies, providing market players with a wide range of information that allows them to improve the performance of their portfolios. Our purpose and value proposition is for our clients to be confident in their own investment decision thanks to our tool, which will deliver all the necessary elements to manage the transactional life cycle for an investment portfolio without infrastructure or lengthy implementations. With that in mind, we also want to be the leaders in the analysis and discussion of the issues that set the tone for the industry from the voice of its main experts and protagonists. On behalf of the entire VMetrix team, I welcome you to this new edition of our Financial Challenge 2022 cycle. Thank you very much. Well, in order to discuss the main points to be addressed in our guest masterclass, we are also joined by Pedro Melo, Country Manager of VMetrix, and Manager of VMetrix, Luis Cineros, Risk Financial Leader Company. Without further ado, we will officially welcome Dr. John C. Hall, Professor of Derivatives and Risk Management at Joseph Lee Rudman School of Management, University of Toronto. Dr. Hall is also co-director of the Master of Finance and Master of Financial Risk Management programs at the Rotman School of Management. Dr. Hall, welcome. The floor is yours.
Hello, it's a pleasure to be here. Today I'm going to be talking about the impact of machine learning on finance. So I'd like to give you a little bit of background to start off. You may well know that I'm probably best known for my research in derivatives. So what made me switch from derivatives to machine learning? This happened about 5 years ago. And I guess there were two main reasons why I got interested in machine learning. The first one was that it was becoming really important in finance. Almost any sort of quantitative application in finance seemed to involve machine learning. This was, maybe about 5 or 6 years ago. And the other thing was that it was becoming really important to my students. And I realized that we had to develop a course in machine learning for our MBA students, our Master of Finance students, our Master of Financial Risk Management students, and so on. So that's how it all came about. And I ended up writing a book on machine learning. Here it is on the screen there. It's not the sort of book you would write for computer scientists. It's the sort of book you would write for business students who want to understand how to work, as it says here, productively with data scientists. So if you want more information on the book, and there's a lot of material that I developed to go with the book, you could go to my website, which is listed there. So what is machine learning? Machine learning is a branch of AI. In fact, artificial intelligence. In fact, many people just think of machine learning and artificial intelligence as being one and the same thing, because machine learning, I think, is by far and away the most important branch of artificial intelligence. So the idea is that we give a computer access to lots and lots of data and just let it learn. The critical word in machine learning is learning. The machine learns from large volumes of data. Many of the methods that we use to learn from data, have been around for a long time. Some even date back to the 1950s, as it says here. What's happened and why we've heard so much about machine learning in the last few years is that computer speeds have finally caught up. Computer speeds and data storage costs have caught up. So many of the tools in machine learning that have been around for some time are now practical tools because the computers, because the machines are fast enough. One thing that I would like to do right at the beginning is sort of draw this distinction between machine learning and automation. Computers, as we all know, have been used to automate many business decisions, sort of many, actually, probably the word decisions is not quite right, but many business activities that otherwise would be handled by human beings, payroll, sending out invoices, summarizing sales by region, all of that sort of thing. And that's all what you could say is digitization, or the third industrial revolution. It's been around for a long time now, and it's pretty much complete. What we're talking about with machine learning is the fourth industrial revolution, as it's called, where computers are not just used to automate activities which would otherwise be handled by human beings, but what they're used is to actually create intelligence from data. So maybe I can illustrate what I'm talking about here with what has become actually a really important application of machine learning, and that is credit decisions or dealing with loan applications. So I got three different situations we could be in here. The first one's a fairly straightforward situation. The loan officers in an organization, they apply certain known rules. Maybe there's a book that lists all the rules they use in deciding whether to accept or reject loan applications. If that were true, of course it's not usually true, but if it were true, then we could automate what the loan officers do, and it would be an application of the third industrial revolution because we know what the rules that human beings use are, and we are just digitizing them. But let's suppose we didn't know what the rules were. Okay, what we might still want to do is to use computers to actually replace some of what the loan officers are doing. And this could be an application of the fourth industrial revolution, because what we could do is to collect data on lots and lots of decisions that the loan officers have made, and data on what the all the information about the loan applicants, what their salary is, what the other obligations that they have are, where they live, whether they own their own house, all those sorts of things. Collect all the information which the loan officer would have and try and find the relationship between the information the loan officer has and the decision the loan officer makes. And that would be an application of the fourth industrial revolution. The computer would be learning how the loan officer actually makes decisions. And then we've got the third bullet point, which goes one step beyond that and say, well, maybe the current rules that the loan officer are using are not the best rules. So maybe we collect a different sort of data. Maybe we collect data on loans and data on how the loans actually worked out. Whether the borrower actually repaid the loan in full or whether they defaulted. And we could try and learn better rules that could be used by the loan officers. And that would be another application of the fourth industrial revolution. Okay, so as I say, the last two bullet points would be the fourth industrial revolution. The first one would be the third industrial revolution. So what, natural thing to do is to talk about machine learning in relation to statistics, because you could say machine learning is the new world of statistics. We have huge data sets, much bigger data sets than we traditionally have had in statistics. There have been these fantastic improvements in computer speeds. So computers can process and analyze the data much faster than they ever could before. And so many of these machine learning tools, as I said earlier, that maybe weren't feasible in the past because computers weren't fast enough, are now feasible. So we can develop nonlinear prediction tools and find patterns in data in ways that were not possible before. But let me say, one thing that you've got to get used to if you work with data scientists is that they have their own terminology. I mean, most fields have their own terminology. So here's some of the terminology that people in machine learning use. They refer to features, whereas traditionally in statistics we've referred to variables. So all the different attributes, for example, of that person who's applying for a loan, like what their salary is, how long they've lived in their current house, all that sort of thing. They're all features. And labels are the values of the outcome, whether the loan turned out to be good or not. And then other things, activation functions, targets, biases, supervised and unsupervised learning, and so on. There's a lot of terminology which, unfortunately, one has to get used to. It took me a while to get comfortable with all this terminology when I first got interested in machine learning. So, you can say that machine learning is the new world of statistics, but there is a difference between what machine learning does and what traditional statistics does. I'm sure many of the people listening have taken a course in statistics at one time or another, probably much more recently than I have. But what you learn in statistics is that the first thing you should do is to sit down and develop a hypothesis about something. Maybe the relationship between inflation and interest rates or whatever it is. You develop a hypothesis. Once you've developed the hypothesis and refined the hypothesis, then you go out and you collect data and test the hypothesis. Machine learning is different. What you do in machine learning is the first thing you do is you go out and collect the data. And then you try different models on that data and you find a pattern, perhaps, if that's what you're interested in, or maybe you're developing some sort of predictive tool like, will this borrower default or will they not default? Okay, but the key point is that you start with the data in machine learning. There's no hypothesis in machine learning. You start with the data and then you try and fit a model to the data. And that, you may say, well, that sounds a little dangerous, and we'll be talking about that in a moment. So sorry, I went the wrong way there. So there's a number of different types of machine learning, and we're going to talk a little bit about each one. So here's a little bit of terminology that you're going to have to get used to when you talk to the data scientists. Unsupervised learning. This might not be, what you would choose as the, if you were defining the terminology for this, you probably wouldn't decide to call it unsupervised learning. But unsupervised learning is all about just finding patterns in the data. For example, you might have, the behavior of all of your customers, and you want to sort of cluster your customers in some way. If you're a bank, you might want to cluster customers so that you know what the next product they're likely to buy is, whether they're going to buy wealth management services, whether they're going to get a car loan, whether they're going to get a mortgage, that sort of thing. So that would be, unsupervised learning, just trying to understand your customers better. Supervised learning is where you're trying to predict something. And there's actually two sorts of prediction, as we'll see. You could be predicting the numerical value of something. Maybe you've got the features of a house in Toronto and you want to predict the value of the house. That's one thing. Or you could be trying to classify the data. You've got all these observations on people who want to borrow money from you, and you want to classify them according to whether they would repay the loan or not repay the loan. Okay, and so those are the two main sorts of supervised learning. You may ask, why is it called unsupervised learning and supervised learning? And as I say, it's not the sort of terminology I would choose. But I think the idea here is that the data scientist, if you're just trying to understand the data better, then you don't have to supervise what the algorithm is doing too much. The algorithm is just going to be looking at the data and coming up with patterns. Whereas if you're trying to predict something, then you've got to supervise what the data is doing so that it actually predicts what it is you're interested in. Reinforcement learning is multi-stage decision making. For example, and we'll talk a little bit about this later, but maybe portfolio management, for example, you take a decision today, the world changes, you rebalance your portfolio tomorrow, the world changes again, and so on. So it's strategy for making a series of decisions. And it's a trial and error strategy. So you do lots and lots of trials and errors and work out what would be a good strategy in reinforcement learning. And we'll talk a little bit more about that later. Let's start with unsupervised learning. So here are some applications of unsupervised learning. I mentioned, you might want to use unsupervised learning to understand your customers better. You may say, well, surely my marketing people understand my customers really well. I don't need a computer algorithm to do it. But actually, it's been shown that, computer algorithms can sometimes enhance your understanding of your customers. Basically, clustering is the main thing you're trying to do. You're trying to cluster your customers according to the data that you have on the customers. And sometimes you maybe even find a new product. There's this little cluster of customers. I hadn't realized that before. Maybe we should think about coming up with a product for that particular cluster of customers. One exercise that I use with my students at Rotman is clustering countries for international investment. I went out and I collected data on different countries, and I'll show you how it came out a little bit later on. But the objective, and I said this is an assignment for students, is to try and cluster countries according to how risky or unrisky they are for international investment. And anomaly detection, if a particular observation doesn't fit into any of the clusters, that could be an indication of an anomaly. So I mentioned this project that I use with students, clustering countries to reflect their risk for international investment. So I actually, downloaded data on 3 different things. There's from the Institute for Economics and Peace, there's something called a peace index. From the Property Rights Association, there's a legal risk index, which tells you, how enforceable your contracts are in a particular country and that sort of thing. And then there's the real GDP growth rate, which, is an indication of how stable the country is, perhaps. Now, you'll find all of those features are measured on different scales. And so one of the first things you always have to do when you're clustering, when you're doing unsupervised learning, is to scale your features so that they're comparable with each other. And the way that I did this was I scaled them so that, they had a mean of 0 and a standard deviation of 1. So they were all comparable to each other. And in this chart on the right-hand side here, you can see that I asked for 3 clusters in this, in this particular test anyway. So there's the high-risk cluster, which minus 1.35 for the peace index. That's because I scaled the peace index, have a mean of 0 and a standard deviation of 1. That means that the countries in this cluster are on average, because this is the center of the cluster here, are on average 1.35 standard deviations below the mean. Okay, they're quite a bit worse than the mean. They're also 0.83 standard deviations worse than the mean as far as the legal risk index is concerned from the Property Rights Association. And they've got pretty bad GDP growth rates as well. They're 1.11 standard deviations below the mean for that. So you can see that this high-risk group are pretty bad on all 3 dimensions. The low-risk group, on the other hand, are well above average on the peace index, the legal risk index, actually a little below average on GDP growth rate, because it turns out that if you're in the moderate risk category, you actually have quite a good GDP growth rate. I might add that Chile ended up in the low risk category as far as this particular study was concerned. But one thing I would say is that all the software is doing is looking at data and saying there seems to be this cluster here, and this cluster here. But it doesn't know how to label the clusters. So you have to label the clusters. And, so this high risk, moderate risk, and low risk are, of course, my labels. And there's no guarantee that those are good labels. Yeah, so there's a certain amount of, human intervention in terms of, interpreting the clusters here. Okay, now let's move on to supervised learning. And as I mentioned earlier, there's 2 categories of supervised learning models. There's when you're predicting the value of something. I gave the example of Toronto house prices. You could be predicting a Toronto house price from the square footage of the living area, the lot size, the number of bedrooms, all that sort of thing. Those would be the features, and you'd be trying to predict what's called the target, which is the price of the house. And basically, how would you do that? You would have some houses which you have labels for. In other words, you know what the prices of those houses are. Maybe they sold recently, and you've got information on that. And so you have some data where you've got feature values and labels, as they're called, which is the value of the target. And then there's others where you're trying to predict the house price. And it's similar on classifying, where, as an example here, whether a loan will default or pay back. Same sort of idea. You've got to have some data, with hopefully quite a lot of data, where you've got data on the features of the loan, and you've got data on whether the loan actually paid back or not. And then you want to make predictions about other loans. Now, what I'd like to talk about next is what one might say is good practice for supervised learning. Good practice is to divide your data into three, so let's suppose you're doing one of the predictive tasks that we've talked about, maybe predicting whether a loan is going to default or not. You've got 10,000 observations. What you will do is to divide those observations into three data sets: training data set, a validation data set, and a test data set. And I mentioned that what you typically do is try out different models in machine learning. So that's what you use the training set for. You say, well, let's try out this model, and we'll estimate the parameters of the model from the training set, which might be 60% of the total data. Then, as all good statisticians would tell you, you have to test your models out of sample. So the validation set, which is separate from the training set, is used to test the particular models that you're looking at out of sample. So, you might have a model that fits the training set really well, but does badly for the validation set, in which case you don't want to use it. Okay, so the validation set is used to test whether the models that you've started with generalize well to a new data set. And then what's the final test data set used for? Well, that's used to provide a final test of how accurate your model is. So you've used the training set and the validation set, and you've chosen a model from, you've chosen a model that's reasonably accurate, that generalizes fairly well to the validation set, but you've kept this test data set, which might be sort of 15-20% of the total, back, and that hasn't been involved in anything you've done with the training set and the validation set, and you use the test data set just to say, well, how accurate is my model? I haven't used this data set in choosing the model in any way, so it's a final out of sample indication of how well the chosen model works. Here's an example that I use with my students. And you can see it's a little baby example. There's only 10 data points, and we're trying to predict the salaries for people in a certain profession, in a certain area, and this is the data you start with. And if you use a fifth order polynomial, this is a fifth order polynomial, you fit the data, as you can see, really well. But common sense would tell you you're overfitting the data, because what we're saying is, as a person gets older, the salary goes down, then it comes up, then it goes down again, then it comes up. That doesn't make any sense. So what you're doing there is you're overfitting, and that's a model that's not going to generalize well to new data, to a new data set. Okay, but then you say, well, why don't I just use a linear model? Well, that's actually going to be underfitting, because you can see there is a tendency for, although we haven't got much data here, there is a tendency for the data to sort of trail off. Sorry, the salary to trail off a little bit as the person gets older. So maybe the best model is the one on the right-hand side here, which is a quadratic model. Okay, so this is a very simple example, but it sort of illustrates that really important, right, not to overfit the data. So the first thing you might ask a data scientist when you're talking about a particular application is, well, can I see the results for the training set and for the validation set? Why did you choose this particular model? And did you test the accuracy of the model on the test data set? It's amazing how many models there are out there which are overfitted and do not generalize well to new data. So it's very important to make sure that whatever model you're talking about with a data scientist does in fact generalize well. So this is kind of a little bit of an illustration of what I'm talking about. This, in these machine learning applications, very often there's some measure of model complexity. It could be, the number of features you're using. In my example that I've just looked at, we had, going from a linear model to a quadratic model to a cubic model and so on. The number of orders of the polynomial could be a measure of model complexity. When we get onto other sorts of models, be looking at neural networks, how complicated is the neural network, and so on. So we've got some measure of model complexity, and what you can see happens with the training set is that, generally speaking, the model error gets better and better as we increase model complexity. Not surprising, because we're going to be, giving the model more scope for fitting the data. Okay, so, in that previous example, whoops, this was fifth order polynomial. It fitted the data really well. If we went up to a 10th order polynomial, it would fit the data even better, because we'd just be giving the data more, just giving it more scope to fit the data. So, as we add more parameters to the model, make the model more complex, then it almost certainly will fit the training set better and better. The question is, what does it do out of sample? What does it do for the validation set once we've fitted the model to the training set? And you can see that, in this this is just a little illustration, but the dotted line here is the model error for the validation set. And it sort of seems to get better and better until about here, and then it starts to, worsen. And so what you could say is, what you're looking for with the model you're choosing is this sweet spot here, which I've labeled X, which is where you've made the model complex up to a certain point, but you know that if you made it any more complex, it would stop generalizing well. Okay, so that's the sort of thing you're dealing with some of these tools that we're talking about here. So I'm going to run through, I haven't got a huge amount of time, so I'm going to run through a number of different prediction tools: linear logistic regression, K-nearest neighbors, decision trees, support vector machines, and neural networks, just to give you a sense of what they're all about. I imagine that most people are familiar with linear regression. Linear regression is not a machine learning tool. It's a tool that statisticians have used for a long time, and we try and minimize the mean squared error. One thing you may have learned in a statistics course is that these independent variables, the ones on the right-hand side of the equation, should be uncorrelated with each other. Now, in machine learning, they're called features, and typically they're not uncorrelated with each other. In machine learning, I mean, if you're predicting the price of a house, you could be talking about the square footage of the living space, the number of bedrooms, the number of bathrooms, and so on. Those are all going to be correlated with each other, no question. So how can we use linear regression when we've got all these correlated variables? And the answer is that machine learning's come up with some special procedures for handling correlated variables. And, without going into details, things like ridge regression and lasso regression are designed to simplify the model and handle correlations to avoid overfitting. So machine learning has come up with some tools to make linear regression a practical tool, even when there are correlations between the independent variables. Logistic regression is designed for the classification problem. So linear regression is designed when you're trying to predict something. Logistic regression is when you're trying to sort of classify, maybe classify your loans into which ones will default and which ones will not default. And basically, the traditional statistics tool for classification is logistic regression. It's very similar to linear regression in many ways. And again, we can use these tools that I mentioned earlier, Ridge and Lasso. Okay, let's talk about another tool. This is actually a very simple tool that machine learning people sometimes use, which is called the KNearest Neighbors tool. Basically, what you've got lots of data. Suppose you're trying to predict the value of a house. You've got lots of data. What you maybe do is to look for a certain number of houses which are most similar to the house you're trying to predict the price of. I mean, my example here is we're using K as the number of similar data items that you look for. So if we use K equals 3, we have 3 nearest neighbors, and maybe they've got prices of, 450,000, 490,000, 440,000. So you just say, well, okay, I predict the price of this house is 460,000 because the 3 most similar houses average 460,000. And that's probably how a real estate agent would do it. Probably the real estate agent, when asked to predict the price of a house, first thing he or she would do is to think, what houses is this house most similar to that I know the prices of? And, we could do the same sort of thing, trying to forecast whether a loan will default. We've got all the features of the loan, what the salary of the borrower is, how long the borrower has lived in their present house, and so on and so on. And you say, well, let's sort of find the 10 loans which are most similar to this loan that we're now looking at. And maybe we'd find that, 2 of them defaulted and 8 repaid. So we'd say there's a 20% chance of a default. So that's the KNearest neighbor. It's a very very similar to how, a human being would approach this forecasting problem or prediction problem. Now, what linear logistic regression, KNearest neighbors do is they consider all the feature values together. Decision trees are different in that they consider the feature values one by one. So you first ask yourself, what's the feature that you know that's got most information content? And then what's the feature with the next most information content, and so on. So this is an example I use with my student. It sort of comes from Lending Club data. Lending Club was a peer-to-peer lender, and they very kindly provided all their data on the web. So it's been, the Lending Club data has been used in lots of, research papers and that sort of thing. But basically you say, well, okay, Lending Club makes all these loans and we see how the loans worked out. What's been the most important feature? If there's one thing that you had to know about a loan, what would it be? And in this particular case, it turns out the debt to income ratio. In other words, what proportion of your income, what proportion of the borrower's income is actually used for existing debt? Okay, and and then you say, well, okay, I'd like to know debt to income ratio. What's the cutoff? I can sort of know whether debt to income ratio is greater than or less than some number. It turns out to be 19.85. And then you say, okay, when I know what the debt to income ratio, whether it's greater than or less than 19.85, what's the next thing that I'd most like to know? It might be you'd like to know a bit more about debt to income ratio, or it might be something else. In this particular example, it turns out you'd like to know the credit score, which, in the US is this FICO score, and so on. And then, you're looking at the income level here, debt to income ratio again here, FICO score again here, and that sort of thing. And then, at the ends of the tree, you have a probability that the loan will work out to be good or not good. Okay, but so the key thing about a decision tree is that you're looking at your features one by one. You're not looking at them sort of all together in the way that you do with, with linear and logistic regression. Okay. Support vector machines, this is another example of some strange terminology, but basically the way support vector machines work is that you imagine, maybe you've got 20 features. What you would try and do is to find a barrier in that 20-dimensional space that separates your observations as well as possible into two groups. This is when you're trying to classify. So, I mean, if you're trying to decide whether loans are going to work out to be good or not, you would say, well, I want to have that, I've got 20 features on each of my borrowers. I would want to have that barrier, if you can think about this, in 20-dimensional space that kind of separates the good loans from the ones that will default. Okay, this is the last one for supervised learning, and it's neural networks. And neural networks are tools, you've probably heard about them, tools for finding any nonlinear relationship. If you've got lots and lots of data, you don't have to assume that a relationship between the thing you're trying to predict and the features, you don't have to assume that it's linear. Could be, and what neural networks do is allow you not to make any assumptions about the nature of the relationship. How does it do this? Well, this is a picture of an artificial neural network. You've got the input layer, which is the values of all of your features. Talk about lots and lots of feature layers in neural networks. You've got the input layer, which is lots and lots of feature values. And you've got the output layer, which are the things you're trying to predict. There might only be one thing you're trying to predict. There might be several things you're trying to predict. Well, the thing about a neural network is you don't go straight from the input to the output. What you do is you sort of have a series of what are called hidden layers. So you try and predict the values in the first hidden layer from the input layer, and then the values in the second hidden layer from the values in the first hidden layer, and so on. So what you're doing in an artificial neural network is splitting the relationship between the target and the features, the output layer and the input layer. You're splitting that relationship into a number of, you could call it sub-relationships, or a number of steps. And you're trying to calculate what the best way or the best architecture, if you like, for going from the inputs to the outputs. Okay, let's now, having rushed through lots of tools for supervised learning, let's now just talk a little bit about reinforcement learning. This is actually my favorite tool because I've used it a lot, actually. I use reinforcement learning to, because I haven't left derivatives completely, and reinforcement learning turns out to be a great tool for coming up with hedging strategies when you've got a derivatives portfolio. So what you're doing in reinforcement learning, as it says here, is you're trying to find a strategy for taking a series of decisions rather than just one. So, take a decision today, the environment changes, you have to take another decision tomorrow, the environment changes again, you'd have to take another decision, and so on. You assume you've got lots of data, and basically you just systematically use a trial and error process for working out what the best strategy is. It's called reinforcement learning because, you may try one strategy and it works really well. So that reinforces you in terms of how good that strategy is. You may try another strategy and that doesn't work out at all well, in which case it reinforces you in the opposite direction. Okay. What are the applications of reinforcement learning? Well, you may have heard about computers being really successful at playing games such as Go and chess. It's been a lot of big history. I used to play a lot of chess when I was younger. There's been a lot of history on computers playing chess. And it used to be the case that in order to get computers to play chess, what you'd do is you'd go to a grandmaster and get the grandmaster to give the computer lots of good strategies to use. and the computer would sort of learn from that. But that's the really best. The best chess playing program right now is something called AlphaZero, which was developed by a subsidiary of Google. And basically, what do? You just tell AlphaZero what the rules of chess are. In other words, you program the rules of chess and nothing more. And what AlphaZero does is it plays against itself many, many times, millions of times, and develops a good strategy. And it's similar thing for Go. Okay, these are very complicated board games, but it's part of the power of reinforcement learning that you just by giving any two-person board game, if you just give the computer the rules of the game, you can use reinforcement learning to become really good. The best chess player in the world at the moment is a Norwegian, Magnus Carlsen, and his chess rating is about 2,800. They have a way of rating chess players. AlphaZero's chess rating is 3,500. So way, way better than the best human chess player. So, I mean, that's sort of just an indication of the power of reinforcement learning. Healthcare is a good application because if you think about how a doctor treats a patient, it is a sequential decision. You try something, you see how it works, you then try something else, and so on and so on. So there's been lots of applications of reinforcement learning in healthcare. Finance applications, optimally selling a large block of shares is an application of reinforcement learning, because you don't want to just dump all, if you're selling a big block of shares, or in fact, for that matter, buying a big block of shares, you don't want to do it all at once, because that will just move the market. So you want to feed your trades into the market little by little, but not too slowly, because the market might move against you. So, that's what reinforcement learning will do for you. It'll sort of monitor what's happening in the market, and you revise your, and come up with an optimal strategy. And in fact, most large portfolio managers use reinforcement learning for that particular decision. Portfolio management is a more general application of reinforcement learning. Most hedge funds making big investments in reinforcement learning these days for portfolio management. And hedging, which is the area I've been working in, it turns out that reinforcement learning can come up with better strategies than we ever had before. Okay, so that brings me to the end. Key issues, that people talk about as far as machine learning is concerned. Explainability is important. It didn't used to be considered important, but it's considered very important today. I mean, if I have an algorithm that makes these credit decisions for me, decides whether you get a loan or not, and you come to me and you say, well, why was I refused for this loan? And I say, well, I can't really tell you, but the algorithm just said no. That's not going to be a very satisfactory answer. So it's important that the algorithms that are used can be understood at some level by the employees who are using the algorithms, and by, in the example I was just giving, and by the customers. And people are very concerned as well about, potential biases in machine learning. You may say, well, surely there shouldn't be any biases as far as computers, but there could be biases in the data that's collected, the way it's collected, the analyst who's, tried out different models and all those sorts of things. But as I've said, it's really important for managers to understand enough about the tools and potential pitfalls of machine learning to work productively with data scientists. One analogy I use here is, why do we teach business students accounting? We don't teach them accounting so that they can become accountants. I mean, some of them might become accountants, but it's really so they can interact with accountants, understand the work product of accountants, the assumptions that accountants make, and that sort of thing. It's exactly the same for machine learning. You know, you've got to be able to interact and work productively with machine, data scientists in the same way as you do with accountants. And there's the sort of interesting question that's talked about from time to time, we're getting better and better at this machine learning, developing artificial intelligence. Can we maintain complete control over it? And, I just leave that as an open-ended question. So thank you very much for listening to me today. And if you've got any questions or comments, I'd be pleased to take them now.
Thank you very much for your presentation, Dr. Howe. We will now continue with the space to answer questions from our attendees. We remind you that you can submit them in the chat box that appears in your Zoom control panel. Here, it's our expert panel of VMetrix to talk about the main key points in our masterclass. Pedro Melo, country manager, is here with us. Luis Cisneros, risk financial lead, and Monica Sanchez, chief revenue officer of the company. And for those who have just joined us, be welcome. I hope you can have the chance to listen to our experts in the second cycle of the webinar. In case you couldn't make it, it will be available in the VMetrix YouTube channel, as well as in the social networks and in our webpage. Let's see the questions for today's panel, and we'll have one for Dr. Hall. The platform incorporating methodologies of machine learning, do they have competitive advantages compared to those which do not have them, and which are disadvantages?
Sorry, there's one thing I didn't quite catch about the question. Whose competitive advantages are we talking about here?
Okay, Dr. Hall, the platforms incorporating machine learning methodologies, do they have competitive advantages compared to those which do not have them, and which are disadvantages?
Yeah, I think machine learning tools are a big advance over the traditional statistical tools that we've used in the past. Big thing is that they can handle large data sets, and speed is an important thing. It was, if we go back if we go back a few years, in fact, computers weren't fast enough to really take advantage of all the tools of machine learning, but they are fast enough now, and they can develop intelligence in the way that just was not possible. It's the difference between, as I said in the presentation, the difference between the fourth industrial revolution and the third industrial revolution. So there's lots of advantages of machine learning over the more traditional tools.
Dr. Hall, regarding machine learning in finance, which are the most developed markets in this matter, currently speaking?
Well, I think machine learning is having an impact on all aspects of finance. You could just give you a few examples. I mean, I mentioned in the presentation credit decisions. I think if you apply for a loan these days, it's almost certain that a machine learning algorithm will make the decision. I think I've worked a lot in the applications of machine learning to derivatives. I think machine learning is having a huge effect on both the pricing and the hedging of derivatives. It's having a huge effect on portfolio management. Even areas such as human resources. If you apply for a job at a large financial institution, almost certainly your resume will be read in the first instance by a natural language processor rather than by a human being. So I wouldn't like to single any one area of finance as being where machine learning is having its biggest impact. I think it's having an impact right across the board, and not just in finance, incidentally, in other areas of business as well.
Thank you very much for your answer. We'll continue with our expert panel we have here, and we'd like to continue asking Luis, since we have a question from the audience, what processes within the investment portfolio management can be automated and enhanced with the use of machine learning? Well, we are considering basically 3 points here, and there might be the investment analysis process, the counterpart risk management, and in investment analysis, we are considering the part that can help decision making of the operators. In counterpart, what we are seeking is to sophisticate the estimation of credit risk, and in the operational risks and validations, as well as minimizing the risks for the companies during the investment process. Thank you very much, Luis. And Pedro, we have one more question. How VMetrix is working on the incorporation of machine learning methodologies for their new software? Well, here for VMetrix, we understand that as a priority. When it comes to the fact of visualizing and understanding that machine learning has an important place in the development. And through this, to develop this value operation for the market, where we can incorporate, based on this, we can incorporate a development path in improving and automatizing those operational processes where we have today validation and non-validation processes, document interpretation, confirmation by incorporating this technology in the enhancement of these processes and automation of those processes that today represent a great importance in the general context of the application. Mainly, I would say that we are working focused on improving this management operational processes within the general context in the transactional life cycle. I just like to add that there are some aspects of risk control focused on price control, detection of unusual operations within the transactional life cycle process, making us be focused on taking these technologies to general processes of our development in the application we are about to launch to the market. Pedro, one more question. What is considered as an unusual operation? I would say that an unusual operation might be understood that that kind of breaks the paradigms or the patterns of an operation with usual features. For example, a customer that in his usual activities is operating in the market for amounts below $500,000 in the spot market, then we see a sudden movement breaking those patterns, and we can see or we detect an operation by this customer above 10 or 5 millions breaking this pattern. And this is why we say there's an alert here, there's a red flag here, in order to take the precautions in the areas that might help us prevent any misuse or mismanagement by this customer. Thank you very much. One more question we have here from the audience. This is for Dr. Howell. Good morning, doctor. You are being greeted from Colombia. What should be first studied if you want to be an expert in machine learning oriented to finance?
What should be first studied? Well, I think first of all, you have to have a good background in quantitative analysis and some knowledge of statistics. So I would say you should, choose a quantitative discipline. It doesn't probably matter too much which one as your undergraduate, for your undergraduate studies. And then take every opportunity to take a machine learning course that you have. As I think I mentioned in my presentation, we now teach machine learning to all of our students at my business school, and other business schools are beginning to do the same thing as well. So there's lots of machine learning courses out there. So you want to start by getting some quantitative background, and then take every opportunity you can to take a machine learning course, maybe a Coursera course. If I think Coursera has a lot of very good courses in this area.
Thank you very much for your answer. We have one more question. Mónica, what is the SAS? Well, an SAS is a solution ready to use, a ready-to-use solution. It's absolutely ready. It's in the cloud. It has all the assets and financial instruments. They are preloaded and pre-configured to operate the portfolio. This is the value proposition VMetrix offers you. Thank you very much, Monica. Dr. Hal, coming back to you. What applications of machine learning can be used for the risk calculation by counterparts?
So the question is, what applications of machine learning are most appropriate in risk management? Certainly, I've mentioned credit decisions, and I think it's now being proved with several, over and over again, that machine learning algorithms are actually capable of taking better credit decisions than human beings. So that's one aspect of risk management that it's a big success story actually of machine learning, and it's one aspect of machine learning. One aspect of risk management that that machine learning's had a really big impact in. Generally speaking, in the derivatives business, hedging a derivatives portfolio is a big activity, a very important risk management activity. I've recently completed a paper which is attracting quite a lot of interest on how you do what's called gamma and vega hedging when you've got a portfolio of derivatives. Most traders keep their portfolio delta neutral on a regular basis, maybe once a day or even more frequently. But gamma and vega are Greek letters which aren't that easy to hedge because hedging gamma and vega involves taking a position in another option, and that's quite expensive. So it turns out that is an ideal problem for machine learning to solve. And we used reinforcement learning and worked out what the optimal strategy for bringing other options into your portfolio when you're hedging gamma and vega. So, I think there's quite a lot of applications of machine learning in risk management, but those are just two that I would mention right now.
Muchas gracias por su respuesta, doctor. Mónica, tú tenías una pregunta también, ¿no?
Luis, ¿cómo nosotros estamos haciendo algo al respecto?
Thank you very much for your answer. Monica, you had a question, right? Luis, how can we do something regarding what Dr. Hal has just explained? We currently have a project we're working on, looking for the most important innovations in counterpart management models, approaching the three types of machine learning. We have tested supervised models, enabling the classification of counterparts, those non-supervised, when we do not have much information, and some regression models to calculate the possible counterparts, and thus incorporate this in the system. All this is linked to a better calculation process with a predictor, CBA, with more sensibility, which is the value fitting, and it will lead to other sensibility product known as SVA, which is a set of valorative fittings incorporating machine learning methodologies. To do this, VMetrix is preparing. There will be a next webinar where we'll particularly refer to these fittings, and you can understand them better. So we'd like to thank everyone for this active presentation in this webinar stage. I guess that we have covered all the questions sent to our chat. Just as the same in the first conference, we would like to give an award to one of our attendees. And since we know that the books of our expert is a very valuable and highly recognized book by our expert, will raffle now the book of machine learning, the same he referred to at the beginning of the lecture. So please send a private message using the same platform with your name and email. The winner will be notified once we finish this event through our social networks. On behalf of all VMetrix team, we thank you for your participation in this second webinar, and now you are invited to connect in December for the last conference of our cycle Financial Challenge, where we listen to the talk of SBA experience as a new sensibility experience of the market, and how its implementation will have an impact on risk management present in investment portfolio by Dr. Hull. And with this invitation, we'd like to end this very important second meeting of Financial Challenge of VMetrix. I think that we now can understand better the mission of machine learning and how financial market can work productively with them. Thank you very much to our expert panel and to all of you for your participation. We are very glad of having shared this important masterclass with all of you during the day in VMetrix, in their social networks. This lecture will be available so that you can share it on your social networks. Thank you very much for joining us, and may you have a great afternoon. Thank you very much.